Hello guys, welcome back. I'm your friend Inside. So today we're going to learn the factors and multiples.
Multiples.
Okay, it's called multiples. Factors and multiples. Let's start from the first one.
What we're going to do in this video are some real quick tests to see if these three random numbers are divisible by any of these numbers here. And I'm not going to focus a lot on the why of why they're divisible. We'll do that in other videos, but really just to give you a sense of how do you actually test to see if this is divisible by 2 or 5 or 9 or 10. So let's get started. So to test whether any of these are divisible by 2, you really just have to look at the ones place and see if the ones place is divisible by 2. And right over here, 8 is divisible by 2, so this thing is going to be divisible by 2. 0 is considered to be divisible by 2, so this is going to be divisible by 2. Another way to think about it is if you have an even number over here, and 0 is considered to be an even number, then you're going to be divisible by 2. So, and over here, you do not have a number that is divisible by 2. This is not an even number, this 5, so this is not divisible by 2. So I won't write any 2 there. So we've gone through the 2's. Now let's work through the 3's. So to figure out if you're divisible by 3, you really just have to add up all the digits and figure out if the sum is divisible by 3. So let's do that. So if I do 2 plus 7 plus 9, actually let me just write it out. Plus 9 plus 5 plus 8 plus 8. What's this going to be equal to? 2 plus 7 is 9. 9 plus 9 is 18. Plus 9 is 27. Plus 5 is 32. Plus 8 is 40. Plus 8 is 48. And 48 is divisible by 3, but in case you're not sure, so this is equal to 48. In case you're not sure whether it's divisible by 3, you can just add these digits up again. So 4 plus 8 is equal to 12, and 12 clearly is divisible by 3. And if you're not even sure there, you could add those two digits up. 1 plus 2 is equal to 3. And so this is divisible by 3. This right over here, let's add up the digits. And we can do this one in our head pretty easily. 5 plus 6 is 11. 11 plus 7 is 18. 18 plus 0 is 18. And if you want to add the 1 plus 8 on the 18, you get 9. So the digits add up to 9. Digits, let me do this so these add up to 9. They add to 18, which is clearly divisible by 3 and by 9, and these two things will add to 9. So the important thing to know is when you add up all the digits, the sum is divisible by 3. So this is divisible by 3 as well. Divisible by 3. And then finally, let's add up these digits. 1 plus 0 plus 7 is 8, plus 6 is 14, plus 5 is 19. Did I do the 8? Yep, 19. So that, we summed up the digits, 19 is not divisible by 3. So this one, we're not going to write a 3 right over there. It's not divisible by 3. Let's try 4. And to think about 4, you just have to look at the last two digits and to see, are the last two digits divisible? Are the last two digits divisible by 4? Immediately you can look at this one right over here, see it's an odd number. If it's not going to be divisible by 2, it's definitely not going to be divisible by 4. So this one's not divisible by any of these first four numbers, these first few numbers right over here. But let's think about this one. 88, is that divisible by 4? And you can do that in your head. That's 4 times 22. So this is divisible by 4. Now let's see, 4 goes into 60 15 times. And then to go from 60 to 70, you have to get another 10, which is not divisible by 4. So that's not divisible by 4. And you could even try to divide it out yourself. 4 goes into 70 1 times. You subtract, you get a 30. 4 goes into 37 times. You multiply, then you subtract. You get a 2 right over here as your remainder. So it is not divisible by 4. Now let's move on to 5. And this is you're probably already very familiar with this. If your final digit is a 5 or a 0, you are divisible by 5. So this one is not divisible by 5. This one is divisible by 5. You have a 0 there. So this is divisible by 5. And this, you have a 5 as your ones digit. So once again, finally, this is divisible by something. It's divisible by 5. Now the number 6. The simple way to think about divisibility by 6 is that you have to be divisible by both 2 and 3 in order to be divisible by 6, because prime factorization of 6 is 2 times 3. So here we're divisible by 2 and 3, so we're going to be divisible by, let me do that in a new color. So we're going to be divisible by 6. Here we're divisible by 2 and 3, so we're going to be divisible by 6. And if you were just divisible by 2 or 3, just one of them, then you wouldn't be able to do this. You have to have both a 2 and a 3, divisibility by both of them. And here you're divisible by neither 2 nor 3, so you're not going to be divisible by 6. Now let's do the test for 9. The test for 9 is very similar to the test for 3. Sum up all the digits. If that sum is divisible by 9, then you're there. Well, we already summed up the digits here, 48. 48 actually is not divisible by 9. If you're not sure, you can add up the digits there. You get 12. 12 is definitely not divisible by 9. So this thing right over here is not divisible by 9. And this one over here, if you added up all the digits, we got 18, which is divisible. It is divisible by 9. And I'm running out of colors, so this one is divisible by 9. All the digits added up to 18. And this one over here, you don't even have to add them up, because we already know it's not divisible by 3. If it's not divisible by 3, it can't be divisible by 8. But if you did add up the digits, you get 19, which is not divisible by 9. So this also is not divisible by 9. And then finally, divisibility by 10. And this is the easiest one of all, because you just have to see if you have a 0 in the ones place. You clearly do not have a 0 in the ones place here. You do have a 0 in the ones place there, so you are divisible by 10 here. And then finally, you don't have a 0 in the ones place here, so you're not going to be divisible by 10. Another way you could think about it, you have to be divisible by both 2 and 5 to be divisible by 10. Here, you are divisible by 5, but not by 2. But obviously,
you know what? I start to think about this kind of question. I used to make such a question in the letter code as an as a programming problem, and they ask us to determine whether a number is let's say is divisible by a number. Okay, so for now we at least know it's something like if it's divisible. If it's divisible by, let's say, 2 or 3, then it's definitely divisible by 2 times 3. Something like that.
See, the easiest one is to just see if you have a 0 in the ones place. What we're going to do in this video are some...
Okay, let's leave it there. This probably not that, useful at all. 3 divisibility rule, what is that?
You're just walking down the street and someone comes up to you and says, quick, 4,792. Is this divisible by 3? This is an emergency. Tell me as quickly as possible. And luckily, you have a little tool in your toolkit where you know how to test for divisibility by 3. You say, well, I can just add up the digits. If the sum of that is a multiple of 3, then this whole thing is a multiple of 3. So you say 4 plus 7 plus 9 plus 2. 11 plus 9 is 20 plus 2 is 22. That's not divisible by 3. If you were unsure, you could even add the digits of that. 2 plus 2 is 4. Clearly not divisible by 3. So this thing right over here is not divisible by 3. And so luckily that emergency was saved. But then you walk down the street a little bit more and someone comes up to you, quick. 386,802. Is that divisible by 3? Well, you employ the same tactics. You say, well, what's 3 plus 8 plus 6 plus 8 plus 0 plus 2? 3 plus 8 is 11, plus 6 is 17, plus 8 is 25, plus 2 is 27. Well, 27 is divisible by 3. And if you're unsure, you could add these digits right over here. 2 plus 7 is equal to 9. Clearly divisible by 3, so this is divisible by 3 as well. And so now you feel pretty good. You've helped 2 perfect strangers with their emergencies. You figured out if these numbers were divisible by 3 very quickly, but you have a nagging feeling because you're not quite sure why that worked. You've just kind of always known it. And so let's think about why it worked. And to think about it, I'll just pick a random number, but we could do this really for any number, but I won't go too proofy on it just so that you can see it's pretty common sense here. And the number we'll use is 498. I could literally use any number in this situation. And to think about why this whole little tool or this little system works, we just have to rewrite 498. We can rewrite the 4, since it's in the hundreds place, we could write that as 4 times 100. Or 4 times 100, that's the same thing as 4 times 1 plus 99. That's all this 4 is. It's 400, which is the same thing as 4 times 100, which is the same thing as 4 times 1 plus 99. And the little trick here is that I want to write, instead of writing 100, I want to write it as the sum of 1 plus something that is divisible by 3. And 99 is divisible by 3. If I had more digits here, 999, 9,999, they're all divisible by 3. And this is why you can do the same reasoning for divisibility by 9, because they're all divisible by 9 as well. Anyway, that's what that 4 in the hundreds place represents. This 9 in the tens place, well, that represents 90, or 9 times 10, or 9 times 1 plus 9. And then finally, this 8, that's in the ones place, that's just 8 times 1, or we could just write plus 8. Now, we can distribute this 4. This is 4 times 1 plus 4 times 99. So it's 4 plus 4 times 99. Actually, let me write it like, I'm going to write, well, actually, let me write it first like 4 plus 4 times 99. Do the same thing over here. This is the same thing as plus 9. Let me do that magenta color. Plus 9 plus 9 times 9. 9 times 9. And then finally, I have this 8 right over here. And I can rearrange everything. These terms right over here, the 4 times 99, and then the 9 times 9. I can write over here 4 times 99. I'll write it with slightly different notation, plus the 9 times the 9. That's those two terms. And then we have the plus 4 plus 9 plus 9 plus 8 plus 8. Well, can we now tell whether this is divisible by 3? Well, these terms, these first two terms, are definitely divisible by 3. This is divisible by 3 because 99 is divisible by 3 regardless of what we have over here. You don't even have to look at this. This is divisible by 3, so if you're multiplying, it's still going to be divisible by 3. This is divisible by 3, so if you're multiplying, this whole thing is still going to be divisible by 3. If you add two things that are divisible by 3, the whole thing is going to be divisible by 3. So all of this is divisible by 3. And if you had other digits here, you would have done the same exact thing. Instead of having 1 plus 99, you would have 1 plus 999, 1 plus 9,999, etc., etc. So the only thing you have to really worry about is this part right over here. You have to ask yourself, in order for this whole thing to be divisible by 3, this part is, well, if that part is, then this part, in order for the whole thing has to be divisible by 3, that also has to be divisible by 3. But what is this right over here? These are just our original digits, 498, 4, a 9, and an 8. We just have to make sure that when we take the sum, divisible by 3. You're just walking down the street, and this part is...
do you know what I was thinking about? I was thinking, oh, mathematics is amazing. Why he could do that kind of transformation to convert this number to this expression, this kind of expression, and extract only the part of critical things, or extract only the important part from that kind of expression to determine the property of this number, or something like that. So this is amazing, although I do not think it's quite useful at all. Okay, let's go on. Factors and multiplies. Let's do an understanding about the factor.
What we're going to do in this video is talk about factors and factor pairs. Now, when we talk about factors, these are really numbers that can be multiplied together to make some number. So, for example, if I were to talk about factors of 6, I could multiply 2 times 3 to get 6. And so we would say that 2 and 3 are factors of 6. In fact, we would also say that 2 and 3 is a factor pair for 6, because when I multiply those two, I can get 6. Now, to think about all of the different factor pairs for a number, we could think about it in terms of area. How can we make a rectangle with area 6? Well, you could do it if it's 2 units by 3 units, so it could look something like this. Hand draw it. So say our rectangle looks like this. So it has 2 rows and then 3 columns. And let's say these all have equal area. It's hand drawn, but you can see that the area here would be 2 times 3, which would be equal to 6 square units. Now, what are other ways to get to an area of 6? Well, you could have something that is 1 row, but then it has 6 columns. So maybe it looks something like this. It looks like this. 1 row, and then you have 1, 2, 3, 4, 5, and I want them all to be roughly the same size. So it's 1 times 6 would be also an area. So that would be another factor pair. We know that 2 times 3 is equal to 6, and we know that 1 times 6 is equal to 6. And these are actually the two factor pairs for 6. And we can do it with larger numbers. We can think about, what about all the factor pairs for something like 16? Pause this video and see if you can think about it. Well, I'll set up a little table here to think about that. And so in this column, I'll put the first factor, and in this column, I'll put the second factor. And the way I like to do it is I start at 1, and I keep working up to the number to try to figure out all of the factors. So let's start with 1. So 1 is definitely divisible into 16. And as long as you put a whole number here, it's going to be divisible by 1. And what do I have to multiply by 1 to get to 16? We'll have to multiply it by 16. So that's a factor pair right there, 1 and 16. Now what about 2? Does 2 go into 16? Well, sure, 2 times 8 is 16. So that's another factor pair, 2 times 8. Found another factor. Now what about 3? Does 3 go evenly into 16? Well, no, 3 times 5 is 15. And 3 times 6 is 18. So 3 doesn't go into 16. So 3 would not be a factor of 16. What about 4? Well, 4 times 4 is 16. So that's a factor pair there. 4 and 4. What about 5? Well, no, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20. 5 does not go evenly into 16. Same thing for 6. 6 times 2 is 12, 6 times 3 is 18, does not go evenly into 16. What about 7? 7 does not evenly go into 16. 7 times 2 is 14. 7 times 3 is 21. What about 8? Well, we already know that 8 goes evenly into 16. You might be tempted to say, oh, there's another factor pair of 8 times 2. But we already wrote that down. We just happen to say that 2 is the first factor and 8 is the second factor, but you could say it the other way around. So we don't have to then go to 8 times 2. And once you've gone halfway, you can be confident that you've already found all the factor pairs. Because then you could go to 9. 9 doesn't go into it. 10, 11, 12, 13, 14, 15. But then 16, of course, is divisible by 16. But we've already written that here in this factor pair. So we have these three factor pairs, 1 and 16, 2 and 8, and 4 and 4.
Okay, that's how they define the factor. It's just two numbers which can be multiplied to a certain number. Then let's have a look at the multiples.
In this video, we're going to start thinking about what it means for something to be a multiple of a number. So we're asked which of the following numbers is a multiple of 9. So pause this video and see if you can figure that out. All right, now let's do it together. And one way to think about a multiple is a number that you can get to by multiplying the number, in this case 9, by a whole number. So we could figure out the multiples of 9 by skip counting. That's one way to do it. So you could go from 9, and then you add 9 to that, you get to 18. You add 9 to that, you go to 27. You add 9 to that, you are going to get to 36. You add 9 to that, 45. Add 9 to that, 54. Add 9 to that, 63. Add 9 to that, you get 72. Add 9 to that, you get to 81. And we could keep going. But to figure out whether these are multiples, you really just have to say, hey, are any of these numbers in this list? Now, if one of these numbers are larger than 81, we would have to keep going to see it's included. But we can see that 46 sits between two multiples of 9. 46, that sits closer to 45, but it sits in there. It sits between two multiples. So that's not going to be a multiple. Another way to think about it is, for something to be a multiple, if you divide by 9, you're not going to get a remainder. But if you divided 46 by 9, you are going to get a remainder. You're not going to be able to divide 9 into it evenly. So I'm going to take that one out of the contention. 77 is right over here. It's between 72 and 81. Once again, it's between two multiples, but not a multiple. 39 is between 36 and 45. So not a multiple, between two multiples, rule that out. And we can see very clearly that 18 is a multiple. If I was doing this on my own, I would just maybe be skip counting in my head. I'd be going 9, all right, I don't see a 9, 18, oh, I see an 18. There you go, especially if I'm only going to pick one choice. Let's do another example.
Okay, that still doesn't answer me the question of what is a multiple.
Multiples.
A number that can be divided by another number without a remainder. A multiple is a number that can be divided by another number without a remainder. Okay, did you understand this? Yes, I did. So it's basically asking for a number. Let's say if we got 4. Will this be a, let's say, multiple? Yes, of course. If you divide it by 2, you will get a whole number with 2. Okay, that's still not so intuitive. Let's do a search. Okay, from the search result, we could at least know. Normally, we would say, is the number a multiple of 2, or is a number is this number a multiple of 3, or something like that. So we will actually specify a specific number for this one. So in the end, if how can we do that check? We just divide that number by 3 or by 2 and say if we could get a remainder or not. If we couldn't get a remainder, that's the multiple, and that's it. If you, let's say, if you still do not understand that, go and check your later mathematics books.
We're told we know that 5 times 3 is equal to 15. Yep, that's true. So which of the following statements are also true? And it says to choose 2 answers. So pause this video and see if you can work through that. All right, now let's go through them one by one. So this first one says 3 is a multiple of 15. Now in order for 3 to be a multiple of 15, that means that we can multiply 15 by some whole number to get to 3. But a multiple of 15, we're thinking 15, 30, 45, it's not going to be 3. What whole number can I multiply 15 by to get 3? If I multiply 15 by 1, I'm already at 15. So this is not going to be our choice. And since they say pick 2 answers, well, we might be able to figure out these. But let's just read them to make sure that they make sense. 15 is a multiple of 3. So that means I could multiply 3 times some whole number to get to 15. And we know what that whole number is. It's 5. They tell us right over there. 5 times 3 is 15. So 15 is a multiple of 3. 15 would also be a multiple of 5 because I can multiply 5 by the whole number 3 to get to 15. So I like this choice. 5 is a factor of 15. Well, factors of a number are numbers that you can multiply together to get that number. So 5 is a factor of 15 and 3 is a factor of 15 because 5 times 3 is 15. So this one is also true. It would have also been true if they said 3 is a factor. If they said 15 is a multiple of 5. Any of those would have been true statements based on what we know, that 5 times 3 is 15.
Okay, that's pretty straightforward. It's just another word for saying that 15 is a multiple of 5 or 1. I guess they're both true. So this is a simple idea. We shouldn't spend that much time on this. Let's go to the next one. Prime numbers. Before we go to the videos, let's just read the definition for the word
prime.
Prime. Okay, that's probably not helpful. Prime number. Okay, it's just a concept about a number, a special kind of numbers. So let's get into it. Let's say what it is.
In this video, I want to talk a little bit about what it means to be a prime number. And what you'll see in this video, or really see in this video, is it's a pretty straightforward concept. But as you progress through your mathematical careers, you'll see that there's actually fairly sophisticated concepts that can be built on top of the idea of a prime number. And that includes the idea of cryptography, and maybe some of the encryption that your computer uses right now could be based on prime numbers. If you don't know what encryption means, don't have to worry about it right now. Just need to know that prime numbers are pretty important. So I'll give you a definition, and the definition might be a little confusing, but when we see it with examples, it should hopefully be pretty straightforward. So a number is prime if it is a natural number, and a natural number, once again, just as an example, these are like the numbers 1, 2, 3. So essentially the counting numbers starting at 1, or you could say the positive integers. It is a natural number divisible by exactly 2 numbers, or 2 other natural numbers. Actually, I shouldn't say 2 other. I should say 2 natural numbers. Not necessarily, it's not 2 other natural numbers, divisible by exactly 2 natural numbers. One of those numbers is itself, and the other one is 1. Those are the 2 numbers that it is divisible by. And that's why I didn't want to say exactly 2 other natural numbers, because one of the numbers is itself. And if this doesn't make sense for you, let's just do some examples here and figure out if numbers are prime or not. So let's start with the smallest natural number, the number 1. So you might say, well, look, 1 is divisible by 1, and it is divisible by itself. You might might say, hey, 1 is a prime number. But remember, part of our definition, it needs to be divisible by exactly 2 natural numbers. 1 is divisible by only 1 natural number, only by 1. So 1, although it might be a little counterintuitive, is not prime. Let's move on to 2. So 2 is divisible by 1 and by 2, and not by any other natural numbers. So it seems to meet our constraint. It has it's divisible by exactly 2 natural numbers itself. That's 2 right there, and 1. So 2 is prime. And I'll circle the prime numbers, circle them. Well, actually, let me do it in a different color since I'll just circle the numbers that are prime. Now let's 3. And 2 is interesting because it is the only even number that is prime. If you think about it, any other even number is also going to be divisible by 2, above and beyond 1 and itself. So it won't be prime. About that more in you. Let's try out 3. 3 is definitely divisible by 1 and 3. And it's really not divisible by anything in between. It's not divisible by 2. So 3 is also a prime number. Let's try 4. Another color. Let's try 4. 4 is definitely divisible by 1 and 4, but it's also divisible by 2. 2 times 2 is 4. It's also divisible by 2. So it actually has, it's divisible by 3 natural numbers, 1, 2, and 4. So it does not meet our constraint for being prime. Let's try out 5. So 5 is definitely divisible by 1. It's not divisible by 2. It's not divisible by 3. It's not divisible by 4. Exactly divisible by 4. You could divide them into a remainder, but it is exactly divisible by 5, obviously. So once again, it's divisible by exactly 2 natural numbers, 1 and 5. So it once again, 5 is prime. Let's keep going just so that we see if there's any kind of a pattern here. And then maybe I'll try a really hard one that tends to trip people up. So let's try the number 6. It is divisible by 1. It is divisible by 2. It is divisible by 3, not 4 or 5, but it is divisible by 6. So it has 4 natural number factors, I guess you could say it that way. So it does not have exactly 2 numbers that it is divisible by. It has 4, so it is not prime. Move on to 7. 7 is divisible by 1, not 2, not 3, not 4, not 5, not 6, but it's also divisible by 7. So 7 is prime. Number 7, and that times 4.
All right, I think that's clear enough. So for this case, we could at least know that a prime number is just a number that is dividable by 1 and itself. Okay, that's the definition of a prime number. That's all we need to know for now. Oh, what is a composite number? That's another classing. Let's just get into it. Oh, here we go. We should get into here.
Determine whether the following numbers are prime, composite, or neither. So just as a bit of review, a prime number is a natural number, so one of the counting numbers, 1, 2, 3, 4, 5, 6, so on and so forth, that has exactly 2 factors. So its factors are 1 and itself. 1 and itself. So an example of a prime factor is 3. There's only 2 natural numbers that are divisible into 3. 1 and 3. Or another way to think about it is the only way to get 3 as a product of other natural numbers is 1 times 3. So it only has 1 and itself. A composite number is a natural number that has more than just 1 and itself as factors. And we'll see examples of that. And neither, we'll see an interesting case of that in this problem. So first, let's think about 24. So let's think about all of the, I guess you could think of it as the natural numbers or the whole numbers, although 0 is also included in whole numbers. Let's think of all of the natural counting numbers that we can actually divide into 24 without having any remainder. We'd consider those the factors. Well, clearly it is divisible by 1 and 24. In fact, 1 times 24 is equal to 24. But it's also divisible by 2. It's also divisible by 2. 2 times 12 is 24, so it's also divisible by 12. And it is also divisible by 3. 3 times 8 is also equal to 24. And even at this point, we don't actually have to find all of the factors to realize that it's not prime. It clearly has more factors than just 1 and itself. So then it is clearly going to be composite. This is going to be composite. Now, let's just finish factoring it just since we started it. It's also divisible by 4, and 4 times 6 had just enough space to do that. 4 times, it is not prime, technically, because it is not, it only has one. It only has one as a factor. It does not have two factors. One is itself, but in order to be prime, you have to have exactly two factors. One has only one factor. In order to be composite, you have to have more than two factors. You have to have one, yourself, and some other things. So it's not composite. So 1 is neither prime nor composite. 1 is neither. And then
Okay, it's clear enough. A composite number is it's a number that has 1 as a factor and also has itself as a factor and also has some other numbers as factors. So that's how they define the composite. What is a prime factorization? What is that?
Write the prime factorization of 75. Write your answer using exponential notation. So we have a couple of interesting things here. Prime factorization, and they say exponential notation. We'll worry about the exponential notation later. So the first thing we have to worry about is what is even a prime number. And just as a refresher, a prime number is a number that's only divisible by itself and 1. So examples of prime numbers, let me write some numbers down. Prime, not prime. Not prime. So 2 is a prime number. It's only divisible by 1 and 2. 3 is another prime number. Now 4 is not prime. 4 is not prime because it's divisible by 1, 2, and 4. We could keep going. 5, well, 5 is only divisible by 1 and 5. So 5 is prime. 6 is not prime because it's divisible by 2 and 3. I think you get the general idea. You move to 7. 7 is prime. It's only divisible by 1 and 7. 8 is not prime. 9, you might be tempted to say is prime, but remember, it's also divisible by 3. So 9 is not prime. Prime is not the same thing as odd numbers. Now, if you move to 10, 10 is also not prime, divisible by 2 and 5. 11, it's only divisible by 1 and 11. So 11 is then a prime number. And we could keep going on like this. People have written computer programs looking for the highest prime and all of that. So now that we know what a prime factorization is breaking up a number like 75 into a product of prime numbers. So let's try to do that. So we're going to start with 75, and I'm going to do it using what we call a factorization tree. So we first try to find just the smallest prime number that will go into 75. Now, the smallest prime number, 2. Does 2 go into 75? Well, 75 is an odd number, or the number in the ones place, this 5 is an odd number. 5 is not divisible by 2, so 2 will not go into 75. So then we could try 3. Does 3 go into 75? Well, 7 plus 5 is 12. 12 is divisible by 3, so 3 will go into it. So 75 is 3 times something else. And if you've ever dealt with change, you know, if you have 3 quarters, you have 75 cents. Or if you have 3 times 25, you have 75. So this is 3 times 25. And you could multiply this out if you don't believe me. Multiply out 3 times 25. Now, is 25 divisible by, you can give up on 2. If 75 wasn't divisible by 2, 25 is not going to be divisible by 2 either. But maybe 25 is divisible by 3 again. So if you take the digits 2 plus 5, you get 7. 7 is not divisible by 3, so 25 will not be divisible by 3. So we keep moving up. 5. Is 25 divisible by 5? Well, sure. It's 5 times 5. 25 is 5 times 5. And we're done with our prime factorization because now we have all prime numbers here. So we can write 75 is 3 times 5 times 5. So 75 is equal to 3 times 5 times 5. We can say it's 3 times 25. 25 is 5 times 5. 3 times 25. 25 is 5 times 5. So this is a prime factorization, but they want us to write our answer using exponential notation. So that just means if we have repeated primes, we can write those as an exponent. So what is 5 times 5? 5 times 5 is 5 multiplied by itself 2 times. This is the same thing as 5 to the second power. So if we want to write our answer using exponential notation, we could say this is equal to 3 times 5 to the second power, which is the same thing as 5 times 5.
It's just wonderful. It's just wonderful to say the definition of the prime factorization, especially that kind of technique that we can use to find that factorization by using a tree-like stuff. In the programming language, we can also do that, the same thing. But before we can using the programming language to write that method down, we need to first know that method first. Otherwise, we will not know what to write, even if we have a great coding skills. Okay, I just want to say more exercise.
We're asked, what is the prime factorization of 36? Let me get my little scratch paper out. So the prime factorization of 36. So let's start with the smallest prime number we know, and that is 2. And think about, does 2 go into 36? Well, sure it does. 36 is 2 times 18. So we can write that down. 36 is 2 times 18. So now we have 36 as a product of a prime number, and 18 is clearly a composite number. It has factors other than 1 and 18. So let's try to factor this further. So is this divisible by 2? Sure. 18 is 2 times 9. 2 times 9. So now 9 is a composite number that we haven't fully factored. Obviously, the 2's are both prime. 9 is not divisible by 2, but it is divisible by 3. 9 is 3 times 3. So we can say that 36 is equal to 2 times 2 times 3 times 3. This is its prime factorization. All of these numbers are prime. So now let's input that.
All right, wonderful. Let's go on. Last common multiple. What is that?
What is the least common multiple of 36 and 12? So, and they say another way to say this is LCM in parentheses 36 and 12. And this is literally saying what's the least common multiple of 36 and 12? Well, this one might pop out at you because 36 itself is a multiple of 12. And 36 is also a multiple of 36. It's 1 times 36. So the smallest number that is both a multiple of 36 and 12, because 36 is a multiple of 12, is actually 36. There we go. Let's do a couple more of these. That one was too easy. What is the least common multiple of 18 and 12? And they just state this with a different notation. What's the least common multiple? Or the least common multiple of 18 and 12 is equal to question mark. So let's think about this a little. So there's a couple of ways you can think about. So let's just write down our numbers that we care about. We care about 18 and we care about 12. So there's two ways that we can approach this. One is the prime factorization approach. We can take the prime factorization of both of these numbers and then construct the smallest number whose prime factorization has all of the ingredients of both of these numbers, and that will be the least common multiple. So let's do that. 18 is 2 times 9, which is the same thing as 2 times 3 times 3. Or 18 is 2 times 9, 9 is 3 times 3. So we could write 18 is equal to 2 times 3 times 3. That's its prime factorization. 12 is 2 times 6. 6 is 2 times 3. So 12 is equal to 2 times 2 times 3. Now the least common multiple of 18 and 12, let me write this down. So the least common multiple of 18 and 12, 18 and 12 is going to have enough prime factors to cover both of these numbers and no more, because we want the least common multiple or the smallest common multiple. So let's think about it. Well, it needs to have at least 1, 2, a 3, and a 3 in order to be divisible by 18. So let's write that down. So we have to have a 2 times 3 times 3. This makes it divisible by 18. If you multiply this out, you actually get 18. And now let's look at the 12. So this part right over here, let me make it clear. This part right over here is part that makes up 18, makes it divisible by 18. And then let's see, 12, we need 2 2's and a 3. Well, we already have 1 3, so our 3 is taken care of. We have 1 2, so this 2 is taken care of. But we don't have 2 2's. So we need another 2 here. So notice, now this number right over here has a 2 times 2 times 3 in it, or it has a 12 in it, and it has a 2 times 3 times 3, or an 18 in it. So this right over here is the least common multiple of 18 and 12. If we multiply it out, so 2 times 2 is 4, 4 times 3 is 12, 12 times 3 is equal to 36. And we are done. Now, the other way you could have done it is what I would say just the brute force method of just looking at the multiples of these numbers. You would say, well, let's see, the multiples of 18 are 18, 36, and I could keep going higher and higher, 54, and I could keep going. And the multiples of 12 are 12, 24, 36, and immediately I say, well, I don't have to go any further. I already found a multiple of both, and this is the smallest multiple of both. It is 36. You might say, hey, why would I ever do this one right over here as opposed to this one? A couple of reasons. This one, you're kind of fun because you're actually decomposing the number and then building it back up. And also, this is a better way, especially if you're doing it with really, really large and hairy numbers. Really, really, really large and hairy numbers where you keep trying to find all the multiples. You might have to go pretty far to actually figure out what their least common multiple is. Here, you'll be able to do it a little bit more systematically and you'll know what you're doing. What is this one? You're kind of, it's
you know what, I can even think about a computing method for this kind of solution. For the first, our function will take two numbers and we will try to get the prime factory chain of each number. When we get the let me use this. When we get the two last, one last, two last, we do a compression. For example, we minus each of these elements from this last, and we will multiply the first last by the last that's left. So in the end, we would get the, let's say, least common multiple in a computational way, or in a way that we could be able to write a program to automatically do that kind of computation. Then again, what is the greatest common factor? It's another concept that we didn't know. Let's just check it out.
We're asked, what is the greatest common divisor of 20 and 40? And they just say, another way to say this is GCD, or greatest common divisor of 20 and 40, is equal to question mark. And greatest common divisor sounds like a very fancy term, but it's really just saying, what is the largest number that is divisible into both 20 and 40? Well, this seems like a pretty straightforward situation because 20 is actually divisible into 40. Or another way to say it is 40 can be divided by 20 without a remainder. So the largest number that is I guess you could say a factor of both 20 and 40 is actually 20. 20 is 20 times 1, and 40 is 20 times 2. So in this situation, we don't even have to break out our paper. We can just write 20. Let's do a couple more of these. So we're asked, what is the greatest common divisor of 10 and 7? So let's now break out our paper for this. So our greatest common divisor of 10 and 7. So let me write. So we have 10. We want to think about what is our GCD of 10 and 7. And there's two ways that you can approach this. One way, you can literally list all of the factors, not prime factors, just regular factors of each of these numbers and figure out which one is greater. So, or what is the largest factor of both. So for example, you could say, well, I got a 10, and 10 can be expressed as 2, or let me be careful, as 1 times 10, or 2 times 5. 1, 2, 5, and 10, these are all factors of 10. These are all, we could say, divisors of 10. And sometimes this is called greatest common factor. 7, what are all of its factors? Well, 7's prime. It only has two factors, 1 and itself. So what is the greatest common factor? Well, there's only one common factor here. 1. 1 is the only common factor. So the greatest common factor of 10 and 7, or the greatest common divisor, is going to be equal to 1. So let's write that down. 1. Let's do one more.
You know what I was thinking about? I was thinking about that we can also write a program for it to automatically get the greatest common factor or divider. You know, first we do first we get both numbers in factorization. I'll get two last. Then we do a comparison. We get the, let's say, common part, and for this one it's 1 and 1. Then we get a third last, a new last, and for this kind of last we get the maxed value out of it. Then that's the value that we want to get as the greatest common factor. This one is simple. And as I think the most basic part for this is to if you want to write such a programming, the basic part is to get the let's say, I forgot the line, so sorry. Oh, here we go. The most important part for your program is to find the prime factorization last for a number. But I guess it's not a hard problem if we really want to make such a software or program or function. Okay, this is basically this is today's learning. In today's learning, we have learned the factors and multiples, and even more, I guess. We also have learned the, let's say, prime number and prime factorization, and the least common multiple, and the greatest common factor or divider. That's what we have learned. Basically, if you are learning it by yourself, you'd better write some notes down. You have to write down those definitions for those concepts. For example, factor, multiples, and all sorts of things that we have learned. You have to write down the concept or definition for that kind of word. Otherwise, you will probably forget all of them later or in the future. But if you write it down, write it into your notes, you can always check it out and do a review so that you can remember it as long as possible. Okay, that's today's learning. I will see you in the next one. Bye.